Hi and hello. Welcome to the lecture series of wireless communication. Myself, M.Naveenraj, uh, Assistant Professor CSE IOT SNS College of Engineering. So this is all about the mobile radio propagation. So we already discussed about how the radio waves are transmitted over the free space and what are the problems it is faced by and what are the attenuations, what are the causes created during the free space traveling. So this is one of the method which is called as knife edge diffraction model. So this is used to estimating the signal attenuation caused by diffraction of radio waves over hills and buildings. So there are a lot of hills and buildings whenever the signal is transmitted from one place to another place. So this knife edge diffraction model is mainly to detect, it is mainly used to detect the radio waves of signal over the hills and buildings. So it is must to detect the radio waves over hills and buildings is predicting the field strength in given service area. So as a starting point, the limiting case of propagation over a knife edge gives you good insight into the order of magnitude diffraction loss. When shadowing is caused by a single object such as building, okay, the attenuation caused by diffraction can be estimated by treating the obstruction as diffracting knife edge. So when starting point you have to calculate the knife edge for the limiting case of propagation into order of magnitude diffraction loss. When shadowing is caused by single subject such as building, attenuation is caused by diffraction that can be estimated using by treating the obstruction as a diffracting knife edge. So whatever the obstacle which is placed in in between the radio waves, that will be cast as a diffracting knife edge. So let's see the example and we can follow how the knife edge diffraction model is performing. Consider a receiver at a point P, okay, at point R. So this R is your receiver, okay, which is located in the shadowing region, okay. The field strength at a point R is the vector sum of the field due to all the secondary hygiene sources in the plane above the knife edge. So after above the knife edges there are so many sources are there that we call as a hygiene sources. So this field there will be some electric field which will be created that due to all these sources. So the above the knife edge there are so many sources in that, so each sources then a field will be created. So that is vector sum of all these will give you the field strength, okay. Next, the difference between direct path and the diffracted path called excess path length, that is del equal to h square by 2 into d1 plus d2 by d1 d2. The corresponding phase difference phi equal to 2 pi del by lambda. That is if you substitute the lambda del value, that is excess path length value, you will get the phase difference, that is 2 pi by lambda h square by 2 into d1 plus d2 divided by d1 d2. So here the Fresnel Kirchhoff's diffraction parameter is used to normalize the phase term and given as v equal to alpha root of 2 d1 d2 by lambda into d1 plus d2. That is the same value, this, okay, which gives phi equal to pi by 2 lambda v square, okay. So where alpha will be equal to h into d1 plus d2 divided by d1 d2, okay. So look at this diagram. So this is the knife edge, that is a diffraction. Now when the radio is transmitting to the expert, then here the Fresnel zones will be there. These are the Fresnel zones, okay. The Fresnel zone represents successive regions where secondary waves have path length from the transmitter which are n times lambda by 2 greater in path length than of the line of sight path. The plane below illustrates successive Fresnel zones, These are the Fresnel zones we call. Okay, this multiple